Hi, this video is a quick introduction to engineering design, contrasting it to other courses you may have taken in engineering. I like to think of engineering design similar to the poem that you may have read in high school, middle school, or elementary school about 6 blind men who encounter an elephant, and every single one of those grabs a different part of the elephant and thinks an elephant is like the part they grabbed because they have a limited perspective on the elephant. And they get to arguing with each other what an elephant is really like. Design is a process about how to see the whole elephant, not narrow down and only see part of the picture. When we talk about engineering design, it's really good to understand what engineering is. And I don't want to spend a lot of time on this, but engineering is a human-mediated process of creating technology through components and systems. We create technology for a function, for a purpose, and we do it through form, how we do it. And design is about making that function through a particular form. We do this because technological systems are able to transform materials, energy, and information. They make the world in which we live in. The functions are provided by components combined into systems. When components utilize physical and scientific phenomena to achieve particular functions. And a lot of your other engineering science classes have been learning about things down on the component levels, like inductors or transistors or whatever. But we build systems. We design systems from a diverse set of components based on need, based on the function we want to perform. And these component functions ideally transfer across systems. In other words, once I design an amplifier module from resistors, capacitors, and transistors, I can use that amplifier in a lot of different applications. And in this way, the systems we design become components. This is the process of abstraction. It's really important in engineering. But the systems we design are always human, social, and technical. And they're going to affect people in society. If we don't remember this, we're evil. Systems designers create ensembles or sort of groups of components that have emergent properties. What this says is that we can't always predict what our designs are going to do, although we need to try. And technological systems evolve. They change over time. We only see one brief moment of design, and we have to plan for our designs to change. Design, the other half of engineering design, is a systematic, intelligent generation and evaluation. Hell, I'm not going to read this. You can read it just as well as I can speak it. The key points is that it's a way, a systematic process to specify things to achieve an objective. And we do this under constraints. So it really is about making things in the real world. A better way to put it is the use of heuristics to cause the best change in a poorly understood situation within the available resources. Heuristics are guidelines or rules of thumb. And so design is a process we use when we want to make a change in the world but don't have godlike powers. I want to spend a bit of time talking about differences between engineering design in your engineering design classes against the more common engineering science classes. Engineering science classes deal with well-defined problems. There's a solution. There are better and worse approaches. You get a better grade if you use a better approach. They focus on finding a strategy to solve a problem, and the problem doesn't change. If you're given a problem on a test, the problem doesn't rewrite itself when you're working on it. In design, however, we're dealing with ill-defined, what are sometimes called wicked problems. It's not always clear what the problem is, so we spend a lot of time trying to figure out how to even frame the problem. The problem, constraints, and solution evolve together. The more we learn about a problem, the more the problem changes because we understand more about what we're really working on. Engineering science problems are convergent. As you work on the problem, you converge toward a solution. When you get a solution, you're done. And we really try to understand the path we took to get to a successful solution so we can use that path over again. Design problems are convergent and divergent. We start by exploring, diverging in our thinking to explore a lot of possible solutions. We pick a solution to work on, but we do that loosely. we don't expect it to be the right solution. We expect the more we work on that solution, the more we're going to learn. And we're going to diverge from that solution. A solution helps us redefine the problem in a better way. So we don't focus on getting to a solution and the right solution. We want to get a solution quickly, realize it's only going to be partial, then rework, revise, and improve. In engineering science, it focuses on analysis. The path to a solution is found by analyzing the problem. In design, it's through iteration. The path to a final solution is through the intermediate solutions we iteratively put out there. Engineering science defines the problem. You match a solution process to a problem type. In other words, once I know what the type of problem is, I know how to solve it. Once I figured out how to do an LCR circuit or Master Kirchhoff's law, then I can use it on all types of problems of that class. In engineering design, it's more important to scope the problem, to learn what the problem is, scope out or explore the possible solution space, and ask if we can change the solution space, because we're allowed to do that in engineering design. So let's look at a particular example you've probably encountered early in your engineering classes or physics classes of a weight on a block and tackle rope and pulley system. If I were to do this type of problem in engineering science, I would ask, what are the forces? Is there friction? Can we assume one gravity of acceleration? We have to know how many times that rope goes through the block and tackle, and then I have to look up the formula I use to solve this type of problem. In engineering design, we have a different set of questions. What's the most weight we'll ever need to lift? Are the pulleys rated for that? Can the beam hold that much weight? How much does the rope cost per meter? Is hand A wearing gloves? Because if they're not, we've got a safety issue. And what if we used an electric winch instead and redefine the problem space that way? In engineering science, key skills are classification. What type of problem is this? Using the language of mathematics to solve the problem. In engineering design, the key skills focus on navigation. How can I iteratively and efficiently move through the problem space? And we use sketches, images, models, prototypes, what we generally call representations, to do that. The big picture looks like this. Within the sciences, including engineering science, we study the natural world through experiment, classification, and analysis. We value objectivity, rationality, and we search for truth. And we produce theories and models that explain the natural world. In the humanities and the social sciences, we study the human world through analogy, metaphor, and evaluation. We value subjectivity, being able to get in there and understand it from the person's perspective, imagination, and we search for justice, and we produce stories that explain to others how the human world works. In design, we study the artificial world through modeling, pattern formation, synthesis, and creation of representations. We value practicality, we value ingenuity, and we search for appropriateness. What's the most appropriate solution under this set of constraints and context? And we produce devices and artifacts. Design is a process. It's a way we go about things. And you've probably seen the design process before. Things that look like this. I'm not going to spend any time on this. And then, of course, there are worse versions that you may have seen in like your first year design course that get more complicated, that are even worse. These have some value because engineering science and engineering design are both part of projects. And projects are cyclical. They do have a set of steps. This is from somebody in Australia that says when we do an engineering project, a design project, we have to identify the client and society needs, conceive of possible solutions, predict the performance of those solutions, and then make an investment, whether we want to basically spend our money on creating it. And if it is a worthwhile investment, we want to deliver a solution on time, at cost, etc., etc. And we only close that loop if we can deliver the project successfully. This is a cycle of engineering practice, and both engineering science plays into different parts of this steps, as well as engineering design. And so you need both engineering science and engineering design to go through the cycle of engineering practice. But design itself does not happen in a cyclical manner. Design is more of a periphery and center of discourse. Discourse, of course, is just talking to other people, having a conversation. And around the perimeter, or the periphery of design decisions, are a whole lot of factors that are going to be important in a design and to different stakeholders in that design. And the thing that connects all these disparate things, like energy use, or the location it's going to be done, how it looks, what the market for the product is, how long it's going to last, is the core of design, which is negotiation. Different people within a company have different perspectives. The clients, the stakeholders have different perspectives. And so the center of design is a process to navigate and negotiate all these different factors that impinge upon a design. And of course, people may have strong opinions as to which is more or less important. So we use a process called rational balancing, or the golden mean, to do this. You can also think of this as a Goldilocks method. And if you remember the story of Goldilocks, she only wanted things that were just right, in the middle between not enough and too much. And we encounter things like this lots of time in our lives. For example, between cowardice and foolhardiness lies courage. It's in between those two extremes. However, what the just right balance is varies. It's contextually dependent. For example, there's a balance in a society between the freedom people have and the security they have in their lives. Too much freedom is a lack of security. Too much security limits freedoms. And certainly events in society, such as a terrorist attack, can shift the society away from freedom and towards security. But as engineers, not everything is completely subjective. There are things like constraints between cost and safety on which our ethical position is that we are willing to have more cost, not to sacrifice safety. In Bucknell, we don't have a cycle of design. We have 8 different perspectives that you have to have in order to be a good designer. And our courses teach these perspectives. And there are other videos that go through this, so I'm not going to talk about all 8 of them here. But at the center of these 8 perspectives is you have to have ideas that you express as representations. Again, these drawings, diagrams, prototypes. And as you negotiate through these representations, you achieve results. You actually move through the process through negotiation. So being able to express your ideas in a form others can understand, and using those to negotiate the process from these 8 perspectives is central to what we do. Another way to look at these 8 perspectives is here. Representations, being able to communicate and prepare your ideas, leads to results. The results in a project, whether positive or negative, lead to increases in your own ability to do design, and that's what's valued in engineers. That's why you're hired, that's why you're paid, that's what makes you a success. Of these 8 perspectives, it's really important to recognize a couple other aspects of it. Some of them involve transferable skills: leadership, empathy, adaptability, transparency, the ability to communicate or work on a team. Others are more focused on technical skills, being able to decompose a problem, break it down into its simpler component parts, doing coding, modeling, measuring, calculating, the building or making of things. And so all these skills are necessary in design. You can focus more on one of these things if that's where your skills lie. In another video we'll talk about that. But they're all necessary for successful design. Another aspect of design is the tensions, and I want to talk about one of those tensions here. Over on the left-hand side, we have prioritized creating a lot of choices for your project, because choices give you freedom. They help you understand the project. They give you options of which to choose to create an optimal or most appropriate solution. But when you start to actually do the design and testing and building, it's really important to prioritize narrowing down your choices to the best options. Though this tension between creating choices and narrowing those choices down is one of the tensions that's central to design. And you'll learn more as you go through design processes and are given design problems. So why do we do engineering design in the first place? This is really important. And what's worth designing? And I want to get a little philosophical on you now and talk about emotions, which is pretty different in engineering because we don't talk about our emotions very much. In Western thought, we incorrectly view emotion as the polar opposite of reason or intellect. But it turns out that it's not intellect that serves as a motive force to act and a guide to what's worth doing in your life. That motive force is emotion, what we care about. And so to value and be able to create things that are good and just, you have to have emotions that are up to this task. You have to have developed emotional maturity. And so in design, because it is about creating things that didn't exist, your emotional development is just as important as your rational or intellectual developments. It turns out there are real emotions and fake emotions. Real emotions arise internally, but we often live in an emotional unreality created by external events. And I want to point out social media here, because the whole point of social media in many cases is to push on your emotions so you generate clicks for the company. So it's really important to know yourself, to know if you're being emotionally manipulated and what's important to you. Similarly, emotions can be for ourselves. We fear for our safety, we fear for our social status, or it can be for others. And the emotions we have toward others and caring for other people are generally more positive. We can turn our emotions into rational observations. I feel this way. But reason and your intellect can't create emotion. You can't think your way to doing good in the world. You need emotional maturity for that. So recognize that emotion is part of design processes. The characteristics of successful designers is they're curious, because being curious helps you get good at being lucky. You need to be able to try stuff, develop a bias toward action. Don't just sit and think. See if your ideas really work. Successful designers are able to reframe problems. This is how you get unstuck and learn to get unstuck, by reframing what you're doing. And the fact that design is negotiation allows this reframing. You have to know design's a process. You have to be aware of that process, where you are in it, and trust the process to get you to the end. And I have a tau in here to represent a time constant, because this process takes time. And you have to sort of accept that things are going to take time, but trust the process is going to get you to a good place in the end. And you have to be willing to ask for help. Practice radical collaboration. There's no way in any design project you personally know enough to get to the end, so seek out those who know more than you do. And these 5 characteristics of successful designers are also characteristics of people who are successful in life. So design becomes practice for a successful life. And I'd like to end on the conversation of working with others. And we can view this on a spectrum, a dynamic spectrum of collaboration. On one end is teamwork, where people work together all the time and share everything. On the other end of that spectrum is working individually and sharing nothing with others. Design usually happens in the middle, a space we call collaboration. You make plans with others, you share the work you're doing, you assign tasks, and you go off and work on those individually, come back, check in regularly. Everybody's contributing individually to the design, but they're collaborating to make the work align with one another. Hopefully this has been informative about design and pointed out some of the differences between design classes and more engineering science classes. You'll learn more by going through the design process.